Look up on a clear night, and the physical sky seems perfectly still. But behind that quiet darkness is a chaotic web of over 5,000 high-speed aircraft moving across the continent at any given second. Most traditional databases store static records. A bank tracks numerical balances. A retailer tracks static inventory. Tracking the national airspace requires a system capable of storing continuous physical motion. Every plane is a constantly updating object with its own altitude, trajectory, intent, and velocity. If a banking database goes offline for a routine update, transactions simply delay. If the database tracking those thousands of airborne flights experiences even a momentary latency spike, human controllers lose the ability to see metal objects converging at 500 miles per hour. Safely managing the sky requires an architecture that actively trades modern software agility for extreme, uncompromising fault tolerance. That architecture is the En Route Automation Modernization System, or ERAM. It is the backbone tracking every high-altitude aircraft in the United States, and it operates strictly as a piece of safety-critical infrastructure, not a cloud application. You won't find it in a commercial data center. ERAM is housed inside 20 sprawling, highly secured facilities across the country, like the Chicago Air Route Traffic Control Center. The reliability standards enforced within these walls mirror the strict computing environments used in nuclear power plants and missile defense systems. It is the heavy machinery of modern aviation, an invisible industrial engine actively routing thousands of flights through the stratosphere. To guarantee zero downtime, incoming data is split simultaneously into two identical processing pipelines, Channel A and Channel B. If Channel A hits an error and stops, Channel D instantly assumes the total output load, continuing without dropping a single packet. Maintaining this parallel processing demands a massive physical footprint. Aisles of dense dual-rack servers run continuously to ensure backup compute power is always active. Beneath that hardware is an environment built on determinism. Instead of relying on standard operating systems, ERAM utilizes legacy Ada code, a language designed specifically to execute unyielding safety logic within strict time constraints. Absolute certainty in aviation means relying on a brute force hardware approach. The FAA willingly trades the efficiency of agile software for hyper-specialized redundancy. Getting the data is only the first step. ERAM instantly ingests a chaotic seed: incoming radar sweeps, ADS-B transponder packets, and real-time weather updates, fusing them into a cohesive picture of the airspace. This interface shows the output of ERAM's trajectory calculations. The vector lines extending from the yellow aircraft data blocks demonstrate the system projecting the physical future of every plane, calculating where flight paths will intersect minutes before they actually do. Those active predictions feed directly to human controllers, who rely on these dense multi-screen stations to navigate the incoming data and avoid converging paths. The national airspace is divided among 20 independent geographic centers. When a flight crosses sectors, ERAM transfers the entire data object, position, intent, and predicted path, to the next center. If one regional center goes completely dark, surrounding nodes continue processing. Data routes around the blind spot. Systemic immortality requires architecting a network where local failures are physically isolated, preventing a regional outage from triggering a national collapse. Maintaining this flawless record has generated staggering architectural debt. ERAM relies on decades of layered patches, customized extensions, and highly specific hardware that becomes harder to source every year. The system has reached its physical and logical limits. It continues to perform its job safely, but the underlying codebase has grown too complex to efficiently maintain or update for modern airspace demands. The FAA is actively transitioning to the Common Automation Platform, or CAP, a massive hardware and software overhaul designed to replace ERAM's aging infrastructure. Until that transition is complete, ERAM remains a living fossil of industrial engineering, a quiet, unyielding machine that successfully predicts the future every second, keeping the sky open.